So, it's okay? Okay, so good morning, everybody. First, I would like to thank the organizer for giving me the opportunity to present this work here. I should apologize a bit since maybe my talk is not on the main topic of the workshop, but still it has to do something with transport, I guess. So I will speak about very recent work which we've done together with Bruno, who is here, and Pavel, who is a PhD student in our group, has been put on the archive like 2 months ago. And yeah, so this work is about chaos, and it's about a model which one can consider as an exactly solvable model of many-body chaos in one dimension. If you think, for example, of your favorite model of quantum chaos, like SYK model, this could be considered as a solvable model of quantum chaos in 0 dimensions. So what we will discuss here is maybe a model which is a simple, really minimal model in 1D, for which you can basically say everything that you're interested in. Maybe everything, I'm not sure, but at least something which is not trivial. I mean, maybe a bit not trivial, you can really compute analytically. For example, there will be few points which I would like to present in this talk. Is first of all, there is a simple measure of chaos which we can use to characterize chaos in many bodies, or in particular in quantum systems in general. This is spectral correlations. So I'll introduce some simple measures of spectral correlations, and then I'll propose this. I mean, not propose, but I'll just outline it in an old conjecture, which I will call quantum chaos conjecture. Some people will call it Bohiga's conjecture. Then I will discuss the model, which is the kicked Ising model, or Floquet Ising model, if you want. It's a driven model. And I will refer to a particular instance of this model, which I will call self-dual. And there is some particular duality transformation in this very simple family of models. And the self-dual points are very special, and they allow for a very strong statements about these models. Yeah. And then, if time permits, I will just give a short, for the flavor, just a short summary of the proof of the, let's say, of the quantum chaos conjecture for this model. Okay, so let me just give you a very short intro into these spectral correlations in quantum systems. So you are, for example, you want to characterize universality in spectral universality in quantum systems. So what you want to do is take a Hamiltonian, you diagonalize it, you take a spectrum, for example, like E sub n, where n is some sequential number. For example, you order the spectrum from ground state to highest excited state, and the number of eigenstates is typically exponential in the volume, in this case in the length, since we are supposed to be in 1D. Yeah, and then you want to say something about this spectrum, yeah, from point of view of statistical mechanics. But first, let's just go to, I will just continue in the Floquet setup, but I would just want to say that in Floquet setup, things are not so much different. I would take, instead of energies, I would take quasi-energies, which are phases. So I would take the periodically driven Hamiltonian system which is periodically depending on time. Then I would take the quasi-energies, which are the eigenphases, that is e to the minus I phi are the eigenvalues of this unitary operator, which is just time-ordered exponential. So, I mean, which is called a Floquet operator. So it's the propagator after 1 unit of time. For example, that period is capital T. So this is the fundamental operator in our business, and its eigenvalues are called quasi-energies. Yeah. And again, you may order them if you want. So this phi n going from 1 to capital N in some order, going from 0 to 2 pi, or then you get mod 2 pi, and everything is periodic on a circle. So this is like a gas of particles living on a box, which is periodic, which has circumference 2 pi, I mean length of 2 pi. Yeah. So, right. Now you want to consider this gas, well, this spectrum of a Floquet Hamiltonian as a gas of particles in a box, and you want to now characterize the statistical mechanics, let's say equilibrium statistical mechanics of this gas. So you want to characterize its 1-point and 2-point functions. Yeah. So 1-point function is simply the spectral density. It's a sum of deltas. And on average, you expect this to be just, I will just put this factor 2 pi over n here, so that the expectation value of this density is equal to 1 by construction. So it's a normalized spectral density. And then, so this is kind of trivial because you don't expect anything. Okay, this is already point of discussion maybe, but you may just take this as an assumption that for sufficiently non-trivial systems, since they are Hamiltonian is extensive in the volume, the quasi-energies are not expected to discriminate any particular value from 0 to 2 pi. So you expect that the density is kind of homogeneous in the interval. Yeah? So at least in thermodynamic limits. So that means that you take this density to be 1 on average, and then you define the 2-point function when you subtract the connected part like this. So then this 2-point function only depends, due to this homogeneity I just described, it only depends on the shift theta, right? So theta is the shift of two spectral variables, and the spectral densities at points phi plus half theta and phi minus half theta, and then you average over phi. Now I don't do any other average apart from averaging over the spectrum, assuming the spectrum is homogeneous, and then I get this 2-point function r of theta. Yeah? So that is the simplest correlation function you can imagine, 2-point correlation function or pair correlation function in the spectrum. And then its Fourier transform is the so-called spectral form factor. So now you just take a simple Fourier transform, right? And then it's like a 2-line calculation, but I drop 1 line from here, but you can do it. I mean, it's like 5-minute calculation. And then you find that this k of t is simply the double sum of the products of the eigenvalues, yeah? Where the other eigenvalue is the conjugated one. So that is basically just the trace of the propagator to power t squared, right? And then there is this connected part subtracted, so that this means this is at t equals 0, there is a delta peak with weight n square, which you subtract. Yeah? So for t positive, you shouldn't even worry about this. So the statement is that the Fourier transform of 2-point function is simply the trace of the propagator square. So if you have a method to calculate trace of the propagator to power t, then basically you can say something about spectral correlations in your many-body system. Okay, so that's sort of the object that we will be calculating, right? So if there's any question, please interrupt me on this point. It should be very elementary and should be completely clear. Okay, so now the problem of this object is this object is very simple-minded. It's very easy to calculate. At least if you have some numerical method, it's very easy. You don't even have to diagonalize the propagator. You just have to take the trace. Well, you have to know how to take products of large matrices. So it is non-trivial, of course, if you don't know anything else about the model. But still, you don't even have to diagonalize it. Yeah. The problem of this object is that it's not self-averaging. So if you compute this for a particular individual dynamical system, then this guy is all over the place. So one has to do some sort of averaging. So what people do is usually, even in random matrix theory, this object, when U is defined as a random matrix, this object, for an instance of random matrix, this object is not well defined. It will not be a smooth function of time. But if you average it over a kind of doing the moving average in time, or if you do average over ensembles of similar systems, or ensemble of random matrices, then this becomes well-defined object, and then you can compute analytical results about this. So we'll have to define some sort of averaging, and I will be specific on the type of averaging when it becomes important. Okay, so now let me just give you a 5-minute introduction to the history of quantum chaos. So as I mentioned, there was this famous conjecture, the quantum chaos conjecture, which has been precisely formulated in this paper by Bohigas, Giannoni, Schmidt. But the conjecture has been previously also kind of hinted in a few other papers, in particular in the paper by Casati and collaborators, and in papers by Berry. And the conjecture says the following: if you have a chaotic system which has a chaotic classical limit, like this chaotic billiards, like this Stadion or Bunimovic billiard, then the quantized, the spectral statistics of the quantum version of the model should obey random matrix statistics. So it should be as random, as eigenvalues of a completely random Hermitian matrices with entries which are Gaussian IIT variables. Actually, that has been already kind of hinted before by Wigner, who introduced random matrix theory in physics, who basically defined random matrix theory as a model to describe complex spectra of, let's say, complex nuclei. This is nuclear data ensemble. So it's just a collection of experimental data about spectral spectra of nuclei, and this is random matrix, this is spectral spacings, this is not spectral form factor but spectral spacings, but indeed you see this Wigner surmise, which is very well fitting the data. But now you do this for the billiard, for example, this is not for the stadium, but it's for this hyperbolic billiard, you find similar or even better quality because you can do nice numerics, right? Even this was even in the 80s. People have found very numerical evidence that this goes very accurately. For example, but on the other hand, when the billiard is not chaotic, like the circular billiard, then the spectral statistic is not random matrix, but it's Poisson. So that's kind of interesting because you have, this spectrum. I mean, arguably you can say that this spectrum is more random than this one because there is no correlations between levels. I mean, Poisson means there is no correlations between levels. So when you have a system which has a lot of structure, like integrable system, then its spectrum is basically structureless. It's Poisson. When you have a system with zero structure, like a chaotic system, then you take its spectrum has a structure, has a rigidity, right? So it's a random matrix, yeah? So that's... okay, so now let's now really seriously compare this to random matrix theory. So in random matrix theory, you can calculate this thing. And now let's go back to our form factor. I mean, now one should maybe spend a few words why people have considered spacings and not form factors in the beginning. Spacings are nice because they're easy to compute, and there is no problem with self-averaging. Yeah? But they are very difficult to do any analytics with the spectra. Spectra are kind of, I mean, if you can express the spacing distribution in terms of pure point functions, and you need all point functions, right? But if, in statistical mechanics, it's easier to compute 2-point functions than 17-point functions, right? So for a theoretician, maybe it's easier to discuss just 2-point functions, yeah? So now let's just go to, just make a small step into many-body quantum chaos, and let's just discuss 2-point functions. So this is basically form factor. So then you can recalculate these things in random matrix theory. It's not too difficult. You look at some monographs on random matrices, like Meta's book, and they will explain you how to do that. For example, there are these ensembles of random matrices, and for Floquet systems, one should take not the Gaussian ensembles, which are the most well-known, but sort of equivalent ensembles for unitary matrices, which are the so-called circular. Sometimes people refer to them as Dyson's circular ensembles, like CUE and COE. So UE refers to now unitary ensemble, which is applicable to systems without any anti-unitary symmetries, like time reversal. And orthogonal ensembles should basically describe systems which have some sort of time reversal symmetry or anti-unitary symmetry in general. So we will be actually discussing systems with time reversal symmetry, so the orthogonal ensemble will be something that we'll need. So you see that this guy has basically expansion in, well, I mean, it basically starts like a linear function of time with the power 2t, and then it saturates around t equal n, where n, well, this should be a curly n, this is the dimension of the Hilbert space, or the number of levels. So this is just a sketch from a recent review. I mean, this is what basically form factor should look like. So there should be this linear ramp, and then there should be a plateau. And then there is a time scale associated to the crossover between the ramp and the plateau, which is the so-called Heisenberg time, which is giving you the dimension of the space, the number of eigenvalues. Then there is a second time scale, which is the so-called Taules time, which is the time scales, the minimal time scale in which random matrix theory is valid. Even in the quantum particle, in the quantum chaos problem of a single particle, I mean, this has been understood by Berry in 1985 that below this time, I mean, this time in quantum chaos has been called Ehrenfest time, and it was related to the logarithm of the effective value of the Planck constant. So below that time, one should really consider system-specific behavior, which is dominated by periodic orbits. Even in chaotic systems, these were the least unstable, the least chaotic short periodic orbits. And so these were basically dominating short-time behavior, and short-time behavior is never random matrix. So there is a time scale, shortest and longest time scales between which you find non-trivial random matrix, universal non-trivial random matrix behavior. So one has to try to understand these time scales in a specific models, yeah? And I'll try to explain what these time scales will be in our specific model. Okay, so please interrupt me if there is any question. So this is kind of intro, and should be really clear. Okay, so now let me just give you one slide of history, how this problem has been treated in single particle semi-classical quantum chaos. So there was the first attempt to understand spectral form factor by Berry in 1985. And he basically used semi-classical, the so-called Gutzwiller-Strace formula, So expansion of classical propagator in terms of sums over periodic orbits, which you simply get from Feynman's path integral, doing stationary phase approximation. Then you get the saddle points of the path integral of classical orbits, and corresponding phases are simply classical actions, and then there's amplitudes, and then this P is just referring to periodic orbit. So since this is trace u to the t square, there should be two sums, right? And then there should be interference effects between these two terms. So basically, very argue that there has to be some sort of random phase approximation of this double sum, so one can simply throw away all the off-diagonal terms because they should average down to 0. So the diagonal, if one just collects the diagonal terms where this phase is exactly cancelled, then one gets this sum of positive terms. And then there is a sum rule, which is called Hanai de Osorio de Almeida sum rule, which is just restatement of classical ergodicity, which tells you that these sums over these weights has to be equal to the length of the orbit. So the length is actually a parameter. So this t actually has to be tau. I'm sorry. This is just a parameter. Okay, so then there could be a factor of 2, which has to do with time reversal symmetry. Namely, one has to pair these orbits, p equal to p prime. But if you have a time reversal symmetry, one has to pair not only p to p prime, but also to its time reversed partner. So there is a periodic orbit and its time reversed partner, and they both exist because of time reversal symmetry. So there's a factor of 2. So sometimes this is referred to a weak localization correction. Okay, so this has been understood in the 80s, but it was very difficult to make progress from here because this is like a leading order. This is like a leading order approximation in this random matrix expansion. You can expand this random matrix result into powers of t for t much less than Heisenberg time, right? And in the first order, you get this Beres term, right? And this can be understood because this is just a short time behavior. For times much longer than that, one has to introduce, for example, for times which become comparable to Heisenberg time, which means for level spacing, because now this translates through Fourier transform to level space to energy scales which are becoming close to level spacings. So when you want to consider level spacing distributions, then you have to understand what happens at times which are not too short compared to Heisenberg, which means you have to understand what happens to high order terms here. Okay, and right, and then it means you really have to start understanding what happens within these interferences. Yeah? And so people had to really, this was one of the main problems in quantum chaos in the 80s and 90s. And it took like 60 years after this seminal paper of Berry that this has been finally understood, at least the first step of this expansion. And there was this really breakthrough paper by Sieber and Richter in 2001, who proposed that one should really consider these pairs of orbits which involve self-encounters. Most of orbits, of course, basically are different when they close. For example, you should consider when the orbits close, and typical orbits would never come close to themselves before they close. But there are some orbits. There is of order of 1 of the Heisenberg time of such orbits, or t over t Heisenberg, for orbits of length t, such that they basically self-meet themselves. I mean, they become close, but they don't exactly close, which means that they necessarily have to come in doublets, right? There are two possible reconnections of these orbits, and they have to have similar classical actions. So there is a very nice semi-classical arguments explaining all that, or classical actually. This is just classical Hamiltonian dynamics, and right. And people understood that, and then basically they put this into this sum, and they found these two actions are similar. There is no exact destructive interference, but there is some constructive effects which can basically be exactly computed, and they give this t-square term here. And then one can do this order by order. So there is a full diagrammatic expansion of this series, which has been completed in the PhD thesis of Sebastian Miller in 2004. And this was basically the final breakthrough. So people have finally understood, at least heuristically, how random matrix appears in quantum chaos of single particle problems. But this is all heuristics. I mean, one has to stress this has never been done to the standards of mathematical physics. This is just explaining the mechanism, because this still is difficult to really precisely prove basically convergence, or even convergence of each particular term of this expansion. And rigorous proof has only been possible for a very specific class of models, which are, for example, one class of models that I'm aware of for which this has been done is the fully connected incommensurate quantum graphs. So I shouldn't go into detail of that. I just tell you that there is a single type of models for which this has been really proven. Okay, but now I think I spent enough time for introduction. So now let me go to many-body systems. So what can one say about I mean, all this is nice kind of nice physics, right? But it requires classical concepts, which means it requires semi-classical limit, which means that there has to be a small parameter which is called effective Planck constant. Yeah? So now the question is, I mean, what about a many-body system where one need not have such small parameter because one has many particles, so one can go to thermodynamic limit without having any effective small Planck constant. Yeah? So what about many-body systems at effective h bar equal 1? Say interacting spin 1/2 particles or fermions. So for example, there is abundant amount of data in the literature. I'm just giving here one figure from the paper by Marcos Rigol and Lea Santos in 2010, but there has been a lot of data since beginning of 90s, showing that random matrix theory should also apply to simple many-body problems, like fermionic problems, without any h-bar, without any small parameter, in thermodynamic limits. So as soon as the model is non-integrable, or sufficiently non-integrable, for example, this is this hopping model where you have next nearest neighbor hopping and next nearest neighbor interaction. So as soon as you switch on either next nearest neighbor hopping or next nearest neighbor interaction, this model ceases to be integrable. So then you go from Poisson to Wigner level spacings. Yeah? So we would like to understand why quantum chaos works in models like this, whereas there is no classical expansion, no semi-classical expansion. So that's the problem. I mean, that's the problem that I was kind of dreaming about since late 90s, and I had no clue how to approach it, and apparently no one else had a clue, so I would now like to report a small progress on this problem. Okay, so now let's just introduce the model. So how am I doing with time, actually? Because okay, so it's okay, good. So now let me just go straight to the model. This is the kicked Ising model, which I will introduce exactly later, but I'll just give you some data on this model, which has been done by, for example, in a paper by Carlos Pineda and myself in 2007. Just to show you how this guy looks. I mean, this is the spectral form factor. Here we call it K2 as a function of scaled time, which is T over T Heisenberg. And this is the model has time reversal symmetry. So you see that this is red is a random matrix, and this sand of points is the numerics. This is just to convince you that this is really a poor thing if you don't do any averaging, right? But then you can either do moving time average. I think this is the black curve. Or you can do basic or you can do averaging over. But I think this is all moving time average. But then these points are different momentum sectors because the model is translation invariant. And then when you average over all momenta, you get this black curve. So you see that you have very nice agreement with random matrix, but only after you do this averaging, moving averaging in time. Otherwise, you don't have anything. And the model has a this is the level spacing. This is integrated level spacing, just to show you that it is really very close to random matrix. You should even go beyond Wigner surmise to see that model agrees with random matrix. Okay, and now let me just go to recent results. So, before I go into details of this recent paper, which I'm going to discuss, let me just mention that there has been some other works with the last few months on the very similar problems. So first of all, there has been another work from our group, I think a more general class of models, but with the less, I mean, we cannot really call this the solution, exact solution, but we just pointed out at the mechanism, which is similar to periodic orbit theory, which one can use in general to derive a quantum chaos conjecture for many body systems with h bar equal to 1. And then there has been two papers by from a group of John Chalker from Oxford, where they also discussed very similar problems, but from the point of view of random circuits. So still non-really, I mean, there is still a small parameter here. For the claims that they make in this paper, there is still a small parameter. It's not exactly h bar, but still there is a small parameter, expansion parameter, where you can argue that quantum chaos emerges. Okay, so now let me really go now to the model. So this is the kicked Floquet Ising or kicked Ising model. So the model is time dependent, is driven. You can think of it like this. This is time dependent Hamiltonian. There is a time independent part, which is just a classical Ising model, and then there is a kick, which is just a transverse field. So you just switch on and off the transverse field in a kicked fashion, or you can think of that half a period you have Ising model, and another half period you have kick or transverse field. So the Floquet propagator, the time ordered exponential, is just simply product of two exponentials. Yeah? So now, I mean, I will imagine now that I have three parameters, so two sets of three type of parameters. There is spin coupling, then there is strength B of a transverse field, and then there is longitudinal field, which I will allow myself still to be random. So I will need some sort of averaging, so I will just introduce some spurious disorder. If you want, I can switch it off at the end of calculation, but at the time being, I will just consider this H8 should be to be some spatially modulated random longitudinal field. And well, this is integrable if, for example, if there is no transverse field. Of course, then it's classical. It's diagonal already in sigma z eigenbasis. It's nothing to do. Or if there is no longitudinal field, then its model can be mapped to free fermions and diagonalized, so it's again integrable. Well, then if you have a clean model, when Aj is equal to a constant, but when all parameters are order 1, this model appears to be ergodic, and spectral statistics is well described in random matrix theory. For example, I showed you a figure from the paper by Pineda and myself from 2007, which suggests that. And then also this model is interesting for those who want to understand, I mean, who don't want, well, there is no understanding, but who want to investigate the transition between ergodicity and non-ergodicity in clean systems. This model has some controversial transition, which is not clear whether it's really a transition, but from numerics it's appeared very clear. For example, if you change parameters, sometimes you see behavior which is very, which is non-ergodic to any time scale that you calculate. Okay, now let me just give you some numerics on this model, and also I'll introduce here the disorder averaging. So what I actually compute now in the simple theoretical model that I'll discuss at the end is the average form factor, where I will average over the disorder. So what you can do here, you can just define the ensemble of systems for the realizations of disorder, and you can introduce disorder to be an IID variable. So any point in space is an independent instance of a random field, and these values of a random field are Gaussian variables with h, with average h bar, that is not Planck constant but h average, and standard deviation sigma, so the magnitude of the strength of disorder sigma. Okay, so now you see, I mean, this is like a Gaussian integral. So now I will use the fact that one can do efficiently Gaussian integrals. But of course, the problem is, if I wanted to do this directly, I mean, you'll see what I mean by that. I mean, but still, just remember how I introduced the disorder here. So, okay, so yeah, so this is just some, some numerical data about this random Floquet Ising model at particular value of couplings, which is j equal to b equal pi over 4, which will turn out to be important later. I mean, this will be exactly the self-dual points, which I will discuss. So at this particular values, you see there is basically no structure in the spectral correlations. This is for, I think, system size, I don't know, 13 or something like that. So the Hilbert space dimension is around 10,000. So I here show just up to 1,000. So you see this is still below, much below Heisenberg time. So there is no curvature of the spectral form factor. This thing is linear, and the slope is 2t. This is just a straight line. The black is straight line 2t, which is the random matrix prediction. And this is just some magnification of the short time behavior. You see what changes from these plots, from this data, is that here we reduce increase the disorder strength. So increasing the disorder strength helps in reducing these fluctuation effects, which anyway, finite size effects, which I could also convince you, but I don't want to show you too much numerics. So this is something for particular system size. If you increase the system size, this fluctuation goes down. In thermodynamic limit, everything just goes straight to the random matrix result, as I will show in a few minutes. I mean, I'll just give you some flash of this result. Okay. So actually, before I'm just wasting all the time, let me just give you the statement. So we basically are able to prove a simple theorem saying that the disorder average spectral form factor for odd times, now we have to make sort of assumption that time is odd for technical reasons. This is equal to 2t if t is larger than 7 and 2t minus 1 for short times. So this is precise. I mean, this is a rigorous result, and it applies to any positive value of disorder strength. So which means I can put a clean limit at the end of calculation. I use the disorder in order to break all the symmetries of the model, because otherwise I would have to worry about translation invariance. But anyway, I mean, and since I do the thermodynamic limit first, any amount of disorder breaks anything I like, but still, disorder is not crucial. There is no transition. There is no MBL transition. I mean, disorder is, I mean, I can put any value of disorder, the model will be ergodic, because showing random matrix statistics is basically a very strong argument of ergodicity. I mean, this cannot be localized. I mean, any localized system would have Poisson-like statistics, like an integral system. So that is a simple statement. And then, of course, since this is only for odd t, I mean, we have basically worked not so too hard because we understand that there are some technical details which are difficult, but still we at least pushed our explicit computations to the limits of our computers. And we have a conjecture for even t, which says that for even t there is a small correction. For t larger than 12, there is probably just a small correction, which is of order 1. So in large time limit is completely irrelevant. But for some short instances like 8 and 10, there is some correction which is order 2. I mean, which is 2t plus 2. So again, I mean, in large t limit, in thermodynamic limit, we conjecture that you have random matrix for even t as well. Okay, so as I already said, probably, I mean, the results are independent of disorder, which means that the model is ergodic, and there is no Floquet MBL in this model. I mean, I should probably be here clear. I mean, this only applies to the self-dual points, which is sigma equal to pi, sigma equal to, j equal to b. So the couplings are all equal to, modulus the couplings is all equal to pi over 4. So, I'm sorry. Okay. Right. So what is also maybe remarkable is that, okay, first of all, there is no disorder, there is no localization transition, and second, results are independent of the average value of the field. So we can even set average value of the field is 0, which means that the reference point is integrable, but any finite amount of disorder breaks integrability in thermodynamic limits sufficiently, so we have random matrices, random matrix behavior. Okay, so yeah, in conclusion, so we found a simple local interacting model with finite dimensional local Hilbert space with proven random matrix spectral correlations at all time scales. Well, here, I mean, I should basically make a disclaimer. It's not fully proven, it's proven for half times. Yeah, but okay. Okay, so now let me just, so the time is, I still don't understand. So I have now 18 minutes left, yeah? Okay, good, so that's perfectly enough. Okay, so so now let me just give you some technical ideas which are crucial to show these statements. So first of all, there is this nice construction of space-time duality. I mean, so now let's see what do we have to compute here. I mean, we have to compute basically traces of the force of the propagator. So this is a spin 1/2 chain, and so time is discrete. So the idea first is to map this trace of the propagator to a partition function of a 2D classical model. So actually this can be done, and actually there is a remarkable identity. I mean, I could even derive it for you in 10 minutes, but I invite you, just if you're curious, just to do it for yourself. It's really straightforward and easy. So what you can do is, but I just write a tensor network for that. So this is just, you know, basically it's a contraction of a 2D tensor network, which you can think of as a partition function of a classical Ising model. So this is a classical Ising model on a lattice which is size T by L. It's a total lattice. It's periodic in time, and it's periodic in space. So there are different, it's an anisotropic Ising model. So there are different spins couplings in the vertical and horizontal directions, and there is external field. So it's not an integrable classical to the Ising model because there is external field, which is important. So you can say, okay, this is again a difficult model, so you cannot really say anything about this, but yes, true. But we can say something about the order average of this model. Okay, so what I have now is a 2D Ising model. This is like you should imagine this is a partition function of 2D Ising model where a field is constant in space, constant in time and varying in space. So that each point is like a classical spin variable, which has also external field and is constant along this light blue line, but it varies vertically. So the values of the field for convenience are indicated as H1 to HL. So this is the longitudinal field, H1Z to HLZ. And now what you can see immediately, if you really try to write down this partition function to all details with all the variables, you can see that basically you can now just shift space and time, because the algebraic, I mean, because you have a partition, you know, it's a classical Ising model, so you can just exchange the values, I mean, of coupling constants. So there is some non-trivial transformation between J and B and some, I would say, dual coupling variables, which I call J tilde and B tilde. Such that this again looks like, well, I mean, it's again classical Ising model. Now, of course, field depends on, is constant well, I mean, you exchange the roles of space and time. So now, instead of, you know, this is the propagator in time, which is the standard flow K-Ising propagator. But now you can imagine this as a propagator is, as powering a matrix, which is a basic transfer matrix in the vertical direction, in the row by row, which I call U tilde. So the idea now is that basically U tilde is of exactly the same algebraic form as quick-Tising model, with just slightly different, well, with different coupling constants, J bar and B bar, J tilde and B tilde. And of course, now for this guy, the field is constant. U tilde has a constant field in time, of course, but the field changes from point to point. Now you see why I can do. I mean, you should now get, you should now get excited, right? Because now what I can do this order averaging, right? Because now this order averaging is, since it's IID, I can do this order average basically step by step. Right? Before it was convoluted inside this guy, and I couldn't do anything, but now I can do it. Okay, but before, of course, I do the disorder average, I have to do the full thing. This is just the trace of the propagator. I have to do the modulo square of the trace of the propagator. So I have to take another copy of the system with a complex conjugation, and then I have to do things all over again. So I will do this in the second slide. Okay, so I have to stress one thing now. Why is this self-duality important? Now, of course, I call now this transformation from U to U tilde duality transformation. And the problem of this duality is that since this U is U operator, this U tilde is in general is not unitary. I mean, this comes from a classical Ising model with complex weights. I do some strange transformation. I map it again to a quantum model, but this quantum model need not be unitary. But at some specific values of the parameters, namely for J, absolute value is equal to B, absolute value is equal to pi over 4, this U tilde happens to be unitary again, which is very nice. So that's why things can be done at this point. Okay, so now what do we do now with the form factor? So actually now we compute the expectation value of the form factor averaged over these longitudinal fields. So what we do now is basically we make two copies, and now we do the product. So this is trace of the U to the T times trace of the U to the T complex conjugate. So the average over field is now our spectral form. I mean, then the multiplication of this guy. But now we average over the field, and we can do the averaging, as I said, averaging as IID, so you can do it step by step. You can do it row by row. So if you do the averaging through, if you pull the averaging through, you just define a simple transfer matrix together with the averaging, such that the spectral form factor is simply trace of this transfer matrix to the power L. Right? So now what one needs to understand, if one goes to thermodynamic limit, is just the spectrum, it's just the leading eigenvalues of this transfer matrix. Actually, for things to converge, the leading eigenvalue of this guy needs to be just 1. If it's less than 1, then this goes exponentially to 0. If it's larger than 1, it blows up exponentially. Since we know that we want to have random matrix, we expect that there is some eigenvalues which are equal to 1, and then some eigenvalues which are less than 1. And why are the eigenvalues less than 1? Because this is supposed to be unitary. Well, I did the averaging. So the averaging is like a contraction. So basically, I can now, then again, this is like a 3-line calculation. You can really do it. It's very simple. You just do this Gaussian average, and this Gaussian average is now a propagate. Now everything, this is like a transfer matrix on a system of size 2T. There is one half which is T, ring T, and another half which is again ring T. So now the unaveraged stuff is simply a tensor product, and then you do the averaging, but the averaging is simply the contraction operation, which is like a kernel of a Gaussian integral. Okay? Some question? I know this is a bit technical, but that's really the idea. It's just, it's okay. So now, so now, as I already said, computation of the spectral form factor now just amounts to determining the multiplicity of eigenvalue 1. So now it so happens that this eigenvalue 1 can have large multiplicity, and this now T is a parameter, time is a parameter, time is the integer. So what we expect that the multiplicity of the eigenvalue 1 should be of the order of T or 2T, because that's what we expect for the form factor. So what we need now to prove or to construct is all the eigenvectors which correspond to eigenvalue 1. So basically we have to determine the dimension of the invariant space of the eigenvalue 1. So that's the proof. And the second part of the proof is, of course, to show that there is a positive spectral gap, so that all the other eigenvalues are separated from 1 by a positive number. This number is strictly positive for positive disorder of for sigma, which is strictly positive for non-zero disorder strand. Okay, so if there is no question here, so I can move on. Now I'll just, okay, so here there is some numerics. I mean, we can show basically, I mean, this is part of the proof to show that the gap is positive. But of course, we have no quantitative result on the gap. So for quantitative results on the gap, we rely on numerics. So we did some numerics with these transfer matrices of t going from 9 to 15 to show, and this is basically the numerical estimate of the gap as a function of the disorder strength. You see that it basically goes like sigma square for small disorder. It opens up at sigma square, and then it saturates for large disorder. So there is a limit, large disorder limit, where the gap becomes independent of the disorder strength. And well, it's nice to have a finite gap, right? Okay, so now let me just go a bit more technical. I mean, just to show you what we really needed to prove. I mean, this is last few slides were simply construction of the method, but then at the end we really have to find these eigenvectors of eigenvalue 1, right? Actually, it's not so difficult to find them. The more difficult thing is to prove that there is no other eigenvectors, so that these are complete set of eigenvectors. So basically, now what we can do is simply do, you can think of this as a vectorization of an operator map, right? I mean, this is like, it's like, when you do open quantum systems, this is like Krauss operator, right, in vectorized form. So now we'll do unvectorization. So basically, each eigenvector associated to eigenvalue 1. So first is to realize that eigenvalues of t, of unit eigenvalue, can either be plus or minus 1. So I will now not intend to show any of this, but these are things which are easy to show. There is one thing which is kind of not so easy to show, but all the simple statements, which I call properties, are easy to show. So the second thing is to show that each eigenvector associated to eigenvalue plus minus 1 is uniquely parameterized by an operator from a Hilbert space of size t. Now this n is equal to t. I'm sorry, this should be t. So now the size of the system is time, right? It's a ring, it's a spin ring of size t. And right, and now unvectorized in an unvectorized form, this should simply satisfy. This should commute or anti-commute with a unitary operator u, and it should commute with all the components of the magnetization. So it should commute with all the SU. Well, it should commute with generators of SU2, and it should also commute with the unitary, which has this particular form. And this unitary is basically one particular instance of our Kick-Teasing model, which is particularly simple. And it can be interpreted, I mean, this is a diagonal unitary, diagonal in sigma z. And it can be interpreted, you see, I mean, this is just counting how many domain walls you have in the periodic arrangements of spins. And this is basically, U is giving you the parity of half number of domain walls. The number of domain walls when you have a periodic arrangements of spins is always an even number. So a half number of domain walls could be even or odd. And this gives you plus or minus 1 for even or odd. So it's a very innocent thing. But it's the minimal thing that you need to include here in order to have 2T solutions of these constraints, right? Otherwise, of course, you have many solutions. If you just want to understand what are the spaces of two invariant operators, there are exponentially many. But then you introduce this extra constraint, you have just 2T of them, right? So this gives you locality. This brings locality of 1D into business, right? It just counts parity of number of domain walls on a ring. Okay. So now, okay, now that's just observation, which gives you all the eigenvectors. And then we have to prove that there is no other eigenvectors. So the observation is the following. Since these operators, U and generators of SU2, are translation invariant and reflection symmetric, that means they commute. And basically, they have to simultaneously commute with all these four guys, right? So, and the generators of the dihedral algebra, right, which is the symmetry algebra of a regular polygon, of n-gon, of t-gon, if you want, which are given as pi to the n, r to the m, where n is either 0 or 1, 0 for t to the 1, and m is 0 or 1, so there is 2t generators, right? And these generators are given in terms of permutations as translation, generator of translation and generator of reflection. So there is exactly 2t of these guys. So there is basically dihedral algebra, which is generated, which is spanned by elements of the dihedral group, which is represented in spin chain of t sides, which gives you the full set of operators which satisfy these properties, right? So this is well, first of all, I mean, it's easy to understand since since these guys are reflection and translation invariant, that any element satisfies this constraint. But now we have to show that there is no other element which satisfies this constraint, right? Okay, so first of all, we need to understand that all these guys are linearly independent, so that in this representation, all the generators of the Hydra algebra are mutually linearly independent. This only happens for times larger than or equal to 6. So there is a simple statement again, which we can show that the number of linearly independent elements of D is 2t for t larger than or equal to 6, and it's 2t minus 1 for t 1, 3, 4, 5, and it's even 2t minus 2 for t equal to. Okay, that's easy to show. And third thing which is easy to show is that for odd times, equation 1, that is this constraint, which is the key constraint, equation 1, can only be fulfilled for eigenvalue plus 1. So which means that for odd times, you can only have eigenvalue plus 1 of this transfer matrix. Okay, that's again not difficult. And then, okay, once you accept all that, then one has to show that all A satisfying 1 are actually given by linear combinations of eigenvalues, of elements of the dihedral group. So these operators which I constructed in the previous slide. And this I will, okay, now this is basically the only non-trivial thing to show. It took us a few months to show that, but I will not enter. I mean, I think I have only 3 minutes left, so I'd like to keep some time for questions. So I can discuss with anyone who's interested the details of the proof. So that's just some table of the multiplicity of this eigenvalue 1 and eigenvalue 1 minus 1. So you see that for even times, there could also be some eigenvalues minus 1, but they are always limited. Because there's always a pair of those, so there's always even numbers of those, and there's just a pair. So for 6 and 10, there's an extra pair of eigenvalues of eigenvalue minus 1, which means that the spectral form factor as a function of time has some oscillatory contribution, right? This is like a, if you want, a kind of time crystal behavior, right? Because the spectral form factor will oscillate with period 2, on top of going around random matrix behavior. Okay, so right, so this is a conclusion. So we believe that we kind of presented the first exact result on ergodicity in terms of spectral correlations for an interacting quantum many-body problem in, let's say, more than 0 dimensions. In particular, self-dual instances of this model provide a minimal model of quantum many-body chaos with no intrinsic timescales. So I didn't stress that yet, but this starts to operate from time equal 1 on, or for time equal 6 if you want. There is some short time specialities, but there is time of order 1 after which this applies. So there's no basically scaling of tauless time, which would be non-trivial in system size. So there is no time scale. So this is a really maximally chaotic system in the sense that there is no intrinsic time scale apart from level density, which is giving you the Heisenberg time. And then there are, of course, I mean, now we got really excited because we see now kind of a couple of different questions which we can address with similar methods. First of all, one has to complete the picture and show also the even T case, but this is really kind of painful, I guess. Then the second pending exciting question is to say anything about the stability of this self-dual point. This is like a particular point in parameter space. We would really like to understand if there is any robustness in the sense, I mean, this is like showing ergodicity for a specific point, but we expect that ergodicity is generic phenomenon, so there should be a way to show that. I mean, it's not like integrability, which is really special, right? This is not supposed to be so special. So there has to be some perturbation theory which has finite radius of convergence with which you could show that this is kind of structurally stable. We don't see how to do it yet, but I kind of think that there should be a way. Well, the more ambitious and far-fetched question is that maybe there is some way to also approach ergodicity MBL transition on the ergodic side using similar ideas. And there is a work actually which we are kind of working on at the moment. We can also use similar ideas to compute dynamics of entanglement entropies via this space-time duality. And again, very kind of ambitious but exciting question is also if one can approach kind of a rigorous proof of ETH, at least for this type of models, also using similar ideas. So with this, I would like to thank for your attention. Yes, I mean, we just made some very rough numerical experiments. Of course, away from self-dual points, there is an indication of MBL. I mean, people have found MBL in the very similar, if not the same models. Yes, but of course, it's very hard to conclude anything from numerics. I mean, numerics is consistent with our claims, let's say, but more than that, it's hard to say.
So I was just wondering how these 2 points sort of fit together. So I guess you expect if you send the sort of disorder to 0, that ergodicity might be sort of stable around this self-dual point.
Yes.
But I guess once there is this disorder and you move away, then I guess you go directly.
If you go away from, yeah, if you do, I mean, you have two knobs. One is
right.
the clean parameters and the dirty parameters, right? If you take clean parameters to go from the self-dual points, then you expect MBL transition if you also introduce disorder, right? But if you just don't move the clean parameters, then there is no transition.
Okay, yeah, thanks.
My question is more about introductory slides, perhaps. So you show this special trajectories, semi-classical analogy. It looked as essential localization physics, correct?
Sorry?
It looked as localization physics.
Yes.
And you made point that it was difficult to figure out and find these orbits. Why it was so difficult? I mean, localization is from 70s. We know much about it. I mean, all of these logs in your spectral function looks like localization type corrections. Yeah,
logs. Where have you seen logs?
Well, in your definition of the spectral form factor K, right? There is this T, which looks like a diffusion.
Yeah.
Previous slide. Yes. So in this orthogonal case, logarithm. I mean,
well, I mean, yeah, but you see, I mean, this is not actually, you know, you should expand the log into power series because there is one here. So there is no log, there is, strictly speaking, no log correction. I mean,
yeah, but I mean, so
even for short T, there is
you
one.
made a point that series with all of these loops is difficult to prove convergence. I have a technical question in a sense that if there is this analogy to localization physics, okay, there are some technical tools, sigma models and everything that sums up all of these loops diagrams. Does this work in here? I
mean, there have been, you know, this was not the point of my talk still, but this was part of introduction. But
yes,
there was a history of quantum chaos problem from, as I say, from 80s to of 90s. There was papers like, there was a very kind of paper which raised a lot of attention in PRL in 1996 by Altschuler and company. Which was debated and was eventually understood to be kind of, well, morally wrong, which used nonlinear sigma model to basically explain the quantum chaos conjecture in partition systems. But as I said, I mean, this has been debated. That has, you know, it's
okay.
It's not
so suppose that I take that self-loop trajectory,
yes,
which is next, as far as I understand, next leading order correction to this 2T.
Yeah, you mean this Sieber-Richter? Oh, sorry.
Yes, so I take this diagram, I compute it in the semi-classical language, and then I compare it to this first term after the expansion of your logarithm. Do they match?
Yes.
Okay, so then the statements that adding more loops, this is the way just to get that logarithm.
Yes.
Okay.
Yeah, yeah. It's just, you know, you want to show that this comes from a clean single particle problem, not from disorder. Yeah, but it's...
Any further questions? Okay, then time for a coffee break and reconvene in half an hour.
We need a